Hello students, now we solve question number 36 from section B. This question multiple select question, so one or more than one options are true. This question is given from group theory and the question is the center ZG of a group G is defined as ZG is equal to X belongs to G such that XG is equal to GX for all G belongs to G. Let mod of G denote the order of G. Then which of the following statements is or are true for any group G? There are four options are given. So let us try to solve this question. So for option A, we take the group G is equal to Q8. The elements of Q8 are I minus I, J minus J, K minus K, L minus L, where I is equal to 2 cross 2 identity matrix 1 0 0 1, minus I is equal to minus 1 0 0 minus 1, J is equal to I 0 0 minus I. Similarly, minus J is equal to minus I 0 0 I. K is equal to 0 1 minus 1 0. So minus K is equal to 0 minus 1 1 0 minus 1 1 0, and L is equal to 0 I 0 minus L equal to 0 minus I 0. These are the elements of the group Q8. So order of Q8 is equal to 8, and Q8 are non-abelian group. Q8 are non-abelian group. The center of G, that means center of the group Q8 is I minus I. Therefore, for the group Q8, order of Q8 is 8 and order of ZG is equal to 2. So G by ZG, order of G by ZG is equal to 8 by 2 is equal to 4 is equal to 2 square. So the quotients group, is of order 2 square, where 2 is prime. Therefore the quotients group G by ZG is abelian, because we know that any group of order p to the p square, where p is prime, then G is abelian. So the group G by ZG of order of g by zg is 2 square, where 2 is prime. So g by zg is abelian. And also we know that the center of an abelian group is the order of the center of an abelian group is equal to the order of the group. So z of g by zg is equal to order of g by zg is equal to 4, which is not equal to 1. So which is not equal to 1. So option A is false. We are taking the same example for group for option D. We are taking for option. So option A is false. We are taking the same example of the group for option D. For option D, we are taking the group G is equal to Q8. That means order of G is equal to order of Q8 is equal to 8 is equal to 2 cube, where 2 is prime. So option D is if order of G is p cube, where p is a prime number, then G is necessarily abelian. But we see that for the group Q8, the order of Q8 is 2 cube, where 2 is prime, but Q8 is non-abelian. So option D is false. Now we check the option B and option C. If order of G is greater or equal to 2, then there exists a non-trivial homomorphism from Z to G. And option C is if order of G greater or equal to 2 and G is non-abelian, then there exists a non-identity isomorphism from G to itself. So first we check option B. For option B, if order of G greater or equal to 2, then there exists a non-trivial homomorphism from Z to G. We know that Z plus is a cyclic group. We know that Z plus is a cyclic group and 1 is the generator. 1 is the generator of the group. So if we take any group G and we fix one element G in G, so for any group G, we take an element, we take any element G belongs to G, we take any element G belongs to G and the generator 1 goes to G. 1 goes to G. So if we consider the homomorphism phi from Z to the group G, where 1 goes to G. Then for any integer n, phi of n is equal to phi of 1 plus 1 plus dot 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 1 n times since phi is a homomorphism, so phi of 1 plus phi of 1 plus dot 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 plus phi of 1 is equal to n of phi of 1, and phi of 1 goes to G, that is phi of 1 is equal to G is equal to Ng for all n belongs to Z. This is a homomorphism. For additive group G, if the group G is a multiplicative group, then phi 1 into 1 into 1 n times phi of n 1 into phi of 1 into phi of 1 dot 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 into phi of 1, that means phi of 1 whole to the power n, that means phi of 1 is equal to G. So the homomorphism, okay, let us write the homomorphism for multiplicative group G. For G multiplicative group, phi of n is equal to phi of 1 into 1 into n times is equal to phi of 1 into phi of 1 into dot 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 phi of 1, that means phi of 1 whole to the power n, that means G to the power n for all n belongs to Z. So if order of G greater equal to 2, then there exists a non-trivial homomorphism from Z to G. This is true, so option B is true. For option C, for option C, for option C, option C is if order of G greater equal to 2, then and G is non-abelian, then there exists a non-identity isomorphism from G to itself. Non-identity isomorphism from G to itself, that means G to G non-identity isomorphism. Non-identity isomorphism from G to G, that means a automorphism from G to G. So since G is a non-commutative or non-abelian group, since G is a non-abelian group, since G is a non-abelian group, there exist distinct elements AB belongs to G such that AB not equal to B. That means AB not equal to B. Therefore, A not equal to BA B inverse. This implies IB of A is equal to B A B inverse not is equal to A. That is IB of A is equal to B A B inverse is an inner automorphism. That is the inner automorphism IB is distinct from the identity automorphism Identity automorphism means non-identity distinct from the identity automorphism, that is non-identity isomorphism. Therefore, if G is non-abelian group, and order of G greater or equal to 2, then there exists a non-identity isomorphism. From G to itself. The non-identity isomorphism is this. This is an inner automorphism, means isomorphism, which is not equal to the identity isomorphism. So option C is true. So there are option B and option C are true. Thank you.